Hi, welcome back to our machine learning course. In this part, we're going to look at one more visualization technique to understand whether the model is learning something good. We've seen an example of a bad model before, where a model had to identify between a husky and a wolf, and it turned out that the model was actually looking at snow in the background to predict whether it was a wolf or a husky. Well, here we're going to learn a new method that will look at the parts of the image that the model is using to make predictions. For instance, in this case, if we have this image of a boy and his dog, and the classification is an Australian Terrier, then hopefully the model is looking at the dog in the image and not at the boy or at the tree outside. And we can do that by taking the activation of a convolutional layer deep in the network. And each activation map will look at certain parts of the image, right? Remember when we were dealing with cats and dogs, the input image, every activation map was looking at something different, right? So this activation map looks at the ears, this one looks at the eyes, this one looks at the background, and so every activation map looks at different parts of the image, right? And we could draw a heat map. We could say, well, this one is looking mostly here, this one is looking mostly here, this one is looking everywhere. And so every input, every activation map, you could convert this basically to a heat map of which parts of the input image is the model looking at, is that activation looking at, right? And then we want to know which combination of activation maps is the model using to make a certain prediction, right? And so we can do that by giving those convolution layers to a gap layer, a global average Boolean layer. So we take the average of all the outputs of the blue activation, the red activation, the green activation, and so on. And we're going to train a model to make a prediction. It has already been trained. And we're going to look at a particular class, Australian Terrier here. And we're going to see what's the influence of each activation layer to my class, right? And then we can take the weighted sum of every activation map times how important that activation map is in making the final prediction. And we take the weighted sum of all of them, and this should give us a heat map of what the model is combined looking at. How the model is combining the activations to make the final prediction, right? So if that is focused on the part of the image that's important, then that's a very good sign that the model actually has learned the right thing. Small caveat is that we won't actually be using the weights, but we'll be using the gradients to do this, right? So this image is a bit misleading. This is how we actually do it in code. So we take our convolutional layer, so I can draw that. We take our convolutional layer, and this convolutional layer will give us an activation map, and it will give us one for every filter. And then, yes, and then that, okay, that's enough. Yeah, then we give this to the gap layer, which will give us one value for every output. So if we have the first activation map, this will result in this average value. This is just the average value of all the values in the activation map. Then we take another activation map, and we average that out. That's going to be our next gap value. We take another activation map, average that out. That's going to be our next activation, and so on, right? Okay, and then in the end, we'll have our final class. And this will be influenced by different of these activation values. We're not going to look at the weights, we're going to look at the gradients. That means the gradients of the loss with respect to the activation layers here. um, that's basically that bit that tells us how sensitive the model is to two particular class X in our output layer. Right? A high gradient would mean that that class is very sensitive to that particular activation map. If the loss would be very low, if the gradients would be very low, then it means that it's not basically very sensitive to it. Okay, so to implement this, we are going to have to write two hooks. One is a forward hook. It's a hook that we attach to this output layer, and this will return us the activations that come out of it. And we'll add a backward hook which will give us a gradient. So every time we do a forward pass to the network, we'll get the activations. Every time we do a backward pass, backward step, we'll get an output with the gradients from our backward hook. Okay, so yes, that's it. So we write our forward hook to return activations. We have a backward hook to return the gradients. We'll attach those hooks to a particular convolution layer. Then we feed forward a particular input image. Yep. That gives us a particular class, right? That's being predicted. Then for that particular class, we're going to do backpropagation. And then, yes, and then we're going to, first of all, get the weights, do the gradCAM weights. So basically, we're going to get the gradients for the backpropagation step. And we're going to take the mean of all the gradients we observe as the weight of that particular activation layer. And then we're going to take the activations, going to weigh them by the weights that we just learned, and sum them up, and that's going to be the heat map. That's a weighted sum. So we're going to, again, take all the activations. Activation 1, activation 2, activation 3. Then we're going to sum it up by a weight 1, weight 2, weight 3, where each weight is basically the sum of all the gradients with respect to that particular activation. It's actually the mean. That's actually divided by the number of steps that we take. Right. Okay, that's it. If we do that, then we get something like this. So here we take a particular input image of the elephants. The class is elephant. Here I plot the top 8 channels, right? So the top activation maps which have the highest weights. And yeah, we can see that they're pretty much looking at the same thing. This one is looking more somewhere else, but most of them are looking at the right thing, right? And if I take the weighted average of all of them and create a heat map from that, then we get this, right? And we see that where blue is high and red is low. And this tells us that indeed, to make the prediction, the model is looking at the elephants. It's not looking at some bird in the sky or anything else. It's really looking at the elephants, right? And yeah, this tells us that the model is actually learning something useful. If I would do the same thing for the class grass, I would hope it will look at the glass. If it have the glass sky, whatever, maybe there's a giraffe in the background, right? Then hopefully it will look at the giraffe and not at the elephants, right? Yeah. So this is a very useful method to identify whether our model is looking at the right thing when it makes the prediction.